Hello and welcome back to High Peak Education. I would like to perform a intuition video about torque and, for that matter, about rotational equilibrium and total mechanical equilibrium and how torque relates to that. I would like to examine torque with several different simulated experiments through many sort of angles, no pun intended. Also, I would like to build some intuition about what this thing called torque is. It's a rotational force. So it's the Newton's law equivalent of force for rotation. However, it doesn't just matter how much force we have. It certainly matters the radius the force exists at and the angle. Let's see if we can examine this with the first experiment that I'd like to perform. What I have here is I have a bolt, which is, let's say, stubborn and hard to turn. And I have a person with a hand, and that hand is exerting a force. We can control the force from the hand. We can control the angle for which the hand exerts the force at relative to the location of the wrench. We can control the distance the hand is away from the bolt, and what ends up being calculated is the so-called lever arm and the torque. And to execute, we have to click apply torque here. So let's go through this one at a time. Notice that if you want to turn this bolt, I think it stands to reason that we need a relatively large force, okay? Especially if it's a very large torque required to turn that bolt. So if we increase the force, we would expect to increase the torque. So that's exactly what we see here. If we increase the force, we do indeed increase the torque. But nothing about the geometry, namely the angle, the distance, the lever arm, or so on, changes. Now notice, we're at about an angle of approximately 140 degrees. So that's approximately the angle here between the wrench horizontally over here and then the person's hand position that the force is linear this direction. Notice, even though 140 degrees is this angle, you could imagine the radius from the axis of rotation, the center of the bolt, to the force. If you dash a line along this wrench, there would be an angle of approximately 50 degrees here. Now, by the way, 50 degrees is often the angle we use, because 50 degrees, which we often call phi, some books certainly call it theta, but I like to call it phi, and phi is the smallest angle between the radius, or for that matter, the radius extended as needed along a dashed line, and the force vector. So in this case, it's about 50 degrees. So I will tell you that, first of all, the sine of 50 degrees multiplied by the distance that we are away here, this 0.19 meters, gives about 0.12 meters. So you can try that in your calculator. You should get that to be the answer, because it turns out that this so-called lever arm is smaller than the distance, that is the radius, we are away from the axis of rotation in general. And it turns out it's reduced by the sine of the smallest angle between those two vectors. In fact, if this was sine of 180 degrees or sine of 0 degrees, it'd be 0. Because if I try to pull this wrench or push this wrench parallel or anti-parallel along or against this direction, there'd be clearly no rotation. There'd be absolutely zero torque. And that'd be a silly thing to do, because we're trying to rotate this bolt. We're not trying to move it linearly. So the sine of the angle makes a big difference. So suppose we try to apply this torque. Now there's insufficient torque to turn the bolt. Let's see if we can make our situation better. If we increase the force, so I want to keep the location the same, but I want to increase the force only. at this 140-degree angle. If we apply this torque, now it's 72.9 newtons. That's a lot more than we had before, but still insufficient torque to turn the bolt. Okay, so even if you pull quite hard, now notice the torque has still gone up. Notice the units of torque are newtons times meters. That's force at a radius. In English units or British units, you might be more familiar with foot-pounds. Foot being distance and pounds being force. But notice the angle and the distance and the lever arm have not changed. So now let's think. Will we say, well, if we want to get this bolt to turn, we shouldn't just have our angle maybe 50 degrees for phi, or 140 degrees here. Let's maybe make our angle 90 degrees, because 90 degrees is exactly perpendicular to the wrench. And I think that the sine of phi will be maximized at 90 degrees. So let's see if we can indeed do that. So let's try to keep our force about the same, but try to rotate our direction here. So now we're able to rotate this. And notice, still with a force of about 77 or so newtons, we now have achieved an angle of 90 degrees. Notice our distance away that we are from the axis of rotation and our lever arm are exactly the same. Notice our torque has now gone up. Now it's 15 newtons times meters. Okay, so let's see if this is sufficient torque to rotate this bolt. Okay, so now the bolt actually turns because we're pulling at 90 degrees. So let's reset, and let's suppose we could only apply a torque at 90 degrees, but suppose our force is only 50 newtons. First of all, if our force is limited, we can't do anything about that. But notice what happens as I increase the radius. As I increase the radius, the torque is getting greater. The distance and the lever arm are remaining the same. That's because the force is exactly perpendicular to the radius. And if we get out here to as large of a radius as possible, we have quite a large torque. So now we have a lot greater ease in turning this bolt. So it seems that torque increases for greater forces, greater orthogonality of angles. So orthogonality means more like a right angle, more like perpendicular, and greater radii. Let's examine this in a slightly different way. So what I have here is I have a solid body, and I have also locations where I can exert forces, and I can change the angle. Notice that when I exert these forces, notice that this right here, this D1, and this right here, D2, are the so-called lever arms or moment arms of the torque. Notice this torque right here looks like, compared to O, and O right here is the location of the axis of rotation of the solid body, this should produce a clockwise torque. I hope you can see that, because the radius goes up, the force goes out that way, and the thumb points into the page by the right-hand rule. So that's clockwise, that's a negative torque by convention. Whereas D2, associated with force 2, is point the fingers downward, that's the radius, the force goes this way, the thumb points out of the screen towards you, and then this right here about this axis is going to give us counterclockwise torque. That's positive torque by convention. Notice I've set the forces differently because I do not think I can change these lengths from the axis of rotation, but I think that we're not going to have any torque in this situation. A 100 Newton force at a small radius and a 45 Newton force at a larger radius balance to be zero total torque. Okay? It turns out actually the torque is very, very extremely small, but it's almost zero. So let's see what we can do, let's say, to increase the clockwise torque. So to increase the clockwise torque, we can change the angle. Notice that if we change the angle, things will change. Okay? So now we have this at 90 degrees, or as close as we can to 90 degrees. So let's give it a shot. So let's go ahead and start. And indeed, notice that we get an angular acceleration because torque is an angular force that creates an angular acceleration. Okay, I hope you see that. Notice if the angle was less than orthogonal, so if the angle was 42 degrees, notice that we'd still get that angular acceleration, but it's not as much as what we had before. Okay, so let's go ahead and reset for a second. Let's go back to this being at 0 degrees and these being roughly in balance. But now let's say we wanted to increase the counterclockwise torque, but we only wanted to do it through forces. Well, force 1 is at its maximum value that's able to be set, 100 newtons or so. But if we increase force number 2, notice that now we're getting greater counterclockwise torque from this force, force 2, compared to the clockwise torque from force 1. So let's start this, and even though in terms of the direction those two angles are balancing each other, the counterclockwise magnitude is larger than the clockwise torque magnitude. So we do get angular acceleration here. So notice that we have this is in radians per second, so this is the angular velocity. So notice the angular velocity is increasing with time because we have a net torque. Okay, so I hope that makes sense. Let's examine torque in a more detailed mathematical way now. So what I have shown here is a turntable. And we're not going to see the motion of the turntable here, but what we're going to be able to examine is we're going to be able to examine the numerical numbers by changing the angle and changing the force impingent upon this point. Notice that we also have an X, Y, and Z axes, and I hope you note the three-dimensional positive axes by the following: that if X is crossed into Y, the thumb points in the positive Z direction. That is, I hat cross product with J hat is the K hat unit vector direction. That is, the right-hand rule of rotating X into Y gives the direction of the positive Z direction. So that's how the axes are set up. Now what we see is we see that we have an angle here of 35 degrees, and then we see that phi is 0.5 degrees. Notice that this radius is going to be at an angle of 34.5 degrees. How do I know that? Because this force vector is just slightly counterclockwise from the x-axis. By the way, counterclockwise we assume is positive torque. It's just slightly counterclockwise from this point and from this position vector, this radius vector that has its tail at the origin and comes out to this point. Notice if phi is positive and not negative, so if we go a few angles back, notice that now phi is negative. But remember, we usually just take phi to be the smallest number between the two vectors. Now, by the way, notice that when phi is negative, we're going to get a slightly negative torque, that is clockwise torque. But when phi is slightly positive, we should get a counterclockwise torque that's roughly, in this case, it's very small. Notice that the torque here is very small because the force is almost exactly parallel to the position vector, the radius position vector. Notice the torque is ever so slightly positive and counterclockwise. So let's imagine what we can do to increase this torque. So suppose we increase the force. Notice that if we double the force, we do indeed get double the torque. But for that much greater of a force, we didn't get really all that much more torque. We got double, but notice that this turntable is not going to rotate very much. If we go back to 50 newtons of force, we remind ourselves, hey, wait, if the angle is roughly perpendicular, so if this initial angle, say, again, 34.5 degrees. Perpendicular to that should be the following. So if we use our calculator, perpendicular to 34.5 degrees, by adding 90 degrees, should be roughly an angle of 124.5 degrees. So let's see if we can get close to that. Notice the torque is going up. So when we get to 124 or so degrees, notice that we now have maximum torque. You can see that these vectors are roughly perpendicular to each other. Notice if we go too far past that point, we still have positive torque, but it's not as large of a torque. If the angle is larger than that optimal angle that we calculated of 124 degrees or so. So this will give us greater amount of torque. Now what if the force is even larger? Well, now we get a really substantial torque, because if we double the force, we get double the torque. Notice the torque vector, remember torque can actually be established as a vector, is given by the cross product of the radius vector and the force vector. And the direction of the torque vector points up along the direction of the rotation axis. In this case, the rotation axis is exactly parallel to the z-axis, and that's because the z-axis comes straight outward, perpendicular to the plane of the xy plane, and it's right above the origin in this case, right above 0, 0 in the xy plane. Okay, what if we wanted to make this torque negative? Well, if we wanted to make this torque negative, the same magnitude torque but negative, it should be clockwise as opposed to counterclockwise. So what we should do is we should take 34.5 degrees and we should subtract 90 degrees, because that's going to give us an angle that's perpendicular to the position vector, but also it's going to give us an angle that's basically going to give us a negative torque. So that's negative 55.5 degrees. So let's see how close we can get to there. Okay. So notice if we go down to 0 degrees here, the phi is negative 34.5 degrees. Now that's not optimal, but it certainly is a larger torque than we had before. So if we wanted to get still even larger magnitude, but still a negative torque, we would increase the force. And again, this turntable should probably rotate clockwise. And remember, clockwise is a negative torque by convention, by this cross product, and by the right-hand rule. Hopefully you now even more deeply understand torque mathematically, even in terms of a cross product. Let's take a look at an important application, namely rotational equilibrium and total mechanical equilibrium for torque. So what we have here is we have two people which are roughly the same mass, thus roughly the same weight, and they're on what you might call a seesaw or a teeter-totter. This seesaw or this teeter-totter allows you to change the ratio of their masses and to change their positions to one another. So let's suppose, for whatever reason, the ratio of the rightward person to the leftward person mass is exactly 1. So they have the same weight, the same mass, and they're the same position away from the fulcrum. And the fulcrum is just going to be the axis of rotation here. So you'd imagine that the total weight down is equal to the total normal or upward support force upward from the fulcrum, and they're in equilibrium. The sum of the forces are equal to 0, and they're not moving nor are they accelerating because their velocity is 0. But suppose that the person on the right-hand side instead is twice as massive as the person on the left-hand side. Well, in that case, notice that the teeter-totter will be out of balance because we have twice as much weight here as we do here. Notice the upward force is still okay, but notice that this is not in rotational equilibrium. Why? Because there's a net torque. There's a net force add a radius to cause this thing to accelerate downward. Notice as this person suddenly gains weight or another person jumps on there, notice that this thing would rotationally accelerate downward on the right hand side, but this is going to be a clockwise torque, which is negative. So we have to add in a counterclockwise torque, which is positive. Now, this person, if we put them 1.5 meters away from the fulcrum, that's not enough because the force is twice as much. We need them to be twice as far away. So if you have this person twice as far away, twice the radius, twice the lever arm. And why the lever arm? Because I think their forces, that is their weights, are exactly perpendicular to their radii. Then we should also have rotational equilibrium again, because twice the radius compared to this person, but then this person has twice the mass compared to this person, twice the force but half the radius, twice the radius but half the force. Those balance in terms of magnitudes, and the positives and negatives cancel out. We are in rotational equilibrium. So now we have this additional version where we can be more quantitative with this seesaw teeter-totter. This point right here is the axis of rotation. We could call that the fulcrum. So we can take these pedestals away and see if this teeter-totter is in balance. Here we also have a ruler showing positions and markers in meters. We have masses with labels, and we can look at the forces on the object, and the green arrows here show us if the object is level or not. So let's go ahead and put, just say a 5 kilogram brick on the right hand side. Notice that should have 5 times 9.8 is about 49 or so newtons of force, that is weight downward. If we remove the pedestals, we do get angular acceleration because we have a torque, because we have a rotational force. So if we reset and we put a 5 kilogram block on the other side and we let the supports go, it should be in balance. So far, so good. So let's instead do the following. Let's instead imagine we have that 5 kilogram block at 1.5 meters. So that's a small angular acceleration, but still yet a net torque. Notice if we put this 5 kilogram block at 1.5 meters, you expect these to be in balance. But notice that if it's at 1.25 meters, it'll only slightly be out of balance. There will be a small angular acceleration. Let's see if we can get this 5 kilogram block balanced at 1.5 meters. So we may ask, well, what if we do a 10 kilogram block? Well, 10 kilogram block, I think it might actually go the other way. Indeed, it does. So we need instead of 5 kilograms at 1.5 for the radius, we need 10 kilograms at 0.75 meters. And that exactly does balance. So there's lots of ways to get this sort of teeter-totter seesaw balanced. Okay? So you can play around with these things. Make sure you understand rotational equilibrium, that the sum of the forces have to be 0 for equilibrium to exist, but the sum of the torques must also be 0 for total mechanical equilibrium. So I want to thank you for watching this video about torque by High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks, and please go ahead and comment below, and I will look forward to seeing your comments. Thank you for watching this video. I will see you in the next video.